upper is equal to u lower, at which gamma dot is 0, steady state. At this point, stagnation is at trailing edge, because the condition is satisfied in the steady case, and you reach your gamma bound, the steady gamma bound. Okay. So this is time. This is rho u gamma bound. We started with a 0 gamma, and we kept increasing. After a while, we're increasing at a slower rate and slower rate until we get to the steady state that is dictated by the brilliant quantum condition. And this process was mathematically described 1925 by Wagner, which we will do in detail in the next lectures. Okay? So it turns out that the lift development over the airfoil, which we learned long time ago in our baby undergrad, was not that trivial. It's actually a very intricate process. Okay? Of course, the Wright brothers did not know all these physics, and perhaps the engineers of Boeing and Airbus, they don't care about all these physics, but I'm sure that in the future, where unsteady aerodynamics will play a great role, we will need to know this physics. Any question about the lift generation, the lift development over an airfoil? It's very, like you said, like you see here, the process is not that easy. It has a lot of physics in it. Okay. Yes, later.
So can you go back to the t equals 0 plus?
Yes.
Can you explain again why there's a huge difference in velocity in the very beginning?
Because the stagnation point in the upper surface and the flow will have to rotate around the corner. We already know if it's an irrotational flow around the corner, the flow goes to infinite at the trailing edge. So the flow coming from the lower surface and rotating will have much higher speed than the flow coming fresh upward on the upper surface. The main issue is that the flow will have to rotate. This rotation is huge, so can you imagine the flow is coming in this direction and you're rotating. So for this to happen continuously, the rotation will have to happen at very, very large speeds. Theoretically, it's infinite speed. Practically, it's very large, but not infinite. And you can see here, this is how they depicted the circulation. How the flow rotates around an edge in general. So this is rotation. This is not T0 plus. This is later in time, but very early, where this is like a starting vortex forming. Okay, here is the starting vortex. So the flow rotates and forming a vortex. Okay, your starting vortex. Now I have a nicer picture here for this one. So here is your starting vortex, and here is the circulation around the bound circulation around the airfoil. And here is later in time. This is later in time. Your starting vortex convects a little bit with the flow, but the structure here of the circulation around the airfoil remains. Do you see this? So this is how the lift develops. Yes, Najib?
When you have separation, you essentially are generating wakes in a wake. Right?
But this is how the wake generated. The difference, though, will be for large separation. You have several options. First of all, you may have separation from the leading edge. So at the leading edge, also it's a sharp. Sometimes it's a sharp edge, even if it's not a sharp edge, but you have a very large angle of attack. When the flow rotates around the leading edge, you create a vortex and it shed away. Sometimes you have separation from the leading edge, and you have two vortices, one coming from the leading edge moving and one coming from the trailing edge moving. Okay? Another thing is that this vortex actually, so let me point out this. I will add a point to your question, but before that, any other question? This is your airfoil, this is your infinity. We have here two boundary layers after a while even. Okay? So we have boundary layer here, boundary layer there. So the vorticity here is something like this. So in operation, while operation actually, you're shedding vortices in the wake continuously. But here is, this is what? Counterclockwise, whatever. This is positive vorticity, this is negative vorticity. For symmetric conditions, you have them cancel each other, and the net vorticity generated in the flow is 0. But when you have unsteady separation, so the conditions are not the same, you have this guy separating early on here maybe, and this guy separating maybe late here. So whatever separates from this point, whatever separates from that point, you subtract them and get what is shed in the wake. Okay, so if you have an unsteady conditions and separation, this separation point actually may fluctuate back and forth. And the same here. It's not easy to characterize mathematically. Okay, so if we back to our question modeling wise, mathematical modeling of unsteady. How to account for unsteadiness in a mathematical model of fluid mechanics model? Well, we just playing the last few lectures with an airfoil, U infinity, steady angle of attack. How we modeled this? Well, we modeled by a single vortex, right? We just learned that if you're gonna account for unsteadiness, at least you're gonna do what? Here is your bound. At least you're gonna do what? What should I add to this to make it an unsteady picture? How to account for this dynamics that I was talking about? What played a major role that you cannot ignore? What played a major role?
The shed.
The what?
The shed vortex.
Yes, this, which we call the starting vortex or the wake vortex, right? Gamma starting, gamma bound. And we just learned in the last lecture that if I want to refine this steady model, I will do what? I will do a distribution of vortices, right? So if this is your plate, I'll do a distribution of vortices. This is your gamma bound. Here I have gamma bound, but it's a function of x, right? Can you make an unsteady version of this? Well, I will do the same at least, right? And this is gamma bound of what? Gamma bound of what? Function of what? Is it function of x? First of all, function of x or not function of x? It's function of x. Function of something else? T. To make it unsteady, right? But also, what? I have to add wake. Gamma wake is a function of x and t. So this is the extension of the linear fold theory that we just studied last lecture, the unsteady extension of it. It's nothing more. Just add a sheet wake, and this guy is unknown also, right? We'll see how to get that. Okay? And if you want to make it more complicated, don't assume that the sheet extends to the x-axis, just assume that the sheet deforms. So this is your vorticity. So this is what we're going to do numerically. Okay? And we can have a three-dimensional version of it. It's the exact same thing, but I don't want to go into it now. Any question? So in conclusion, if you want your model to account for unsteadiness, it's wake. So this was a debate actually between me and one of the, if you want to say, experts in the field. I believe in this, and I believe that it's correct 100% that unsteadiness is equivalent to wake effects, equal to wake effects. If you're accounting for your wake, your model is unsteady. If you're not accounting for the wake, Your model is not unsteady, period. Okay? Any question? Okay, so we are deep into unsteady Aero. We're going to do some math modeling today. We're going to do Tudorson. Of course, we'll not be able to finish it, but we'll start Tudorson, the most famous unsteady aerodynamic model. So first of all, Tudorson did the frequency response. What is frequency response? It's just frequency response concept in dynamical systems. So if we have a transfer function, if we have a state space model, if we have the step response, they are all equivalent. And I mentioned one more, which is called the frequency response. Just let us review it quickly. So if you have a linear system transfer function g of s and you give it an input, it's a sinusoidal input, a cosine omega t. So I'm continuously changing. I get also a sinusoidal output because it's a linear system. And it's the same frequency, the same speed. Okay? So, I'll give you an example, but anyway, so if you have your airplane and you're playing with the elevator, slowly the airplane will change slowly. If you're playing it with the elevator fast, the airplane will follow you fast. And you can imagine that if I play with the elevator too fast, the airplane might not feel anything, right? This is exactly the frequency response. So ideally, your output will oscillate at the same speed. It's a linear system, but with a different amplitude b. It's not the same amplitude anymore, and with some phase shift. So let's look at this here. So if this is your input, u, and if it's a sine wave, okay, some speed and amplitude, so this is your A. This is my output. Y as a function of time. At the beginning, as soon as I apply my input, at the beginning there will be whatever, I don't care about it, transient. There always will be a transient. In the step response, everything is contained in the transient because the steady state doesn't tell you anything about the dynamics, right? So when you apply 5 degrees elevator step, and the airplane oscillates a little bit and gets some angle. The value of this angle doesn't tell you anything about the dynamics. What tells you about the dynamics is the transient of a step input. But when you give a sinusoidal input, we typically ignore the transient, so I don't care about it. So this is my peak. This is different from A. It's another amplitude, and it occurs at a different time. So this is the T lag, the lag time. Okay, my peak occurs later. It's not at the same time as the peak of the input, and this is related to phi. So phi, as Anshin was asking, the phase shift affecting your lag. Okay? Your system is slow in response, will have much lag, will have very negative, large negative phase difference. Okay? Okay, so it's very intuitive to think that B and phi, since this is for any linear dynamical systems, it is very intuitive to think that, okay, your system will affect the output amplitude B and the phase shift phi. So whether it's a car, airplane, submarine, or an oven, every system will have its own B and phi, right? In other words, the transfer function G will dictate this B and phi, and this is of course true. And turns out to be, so this B over A is actually the magnitude of your transfer function. and the phase is the angle of the transfer function. So your transfer function is a function of s in the s domain. Just replace each s by j omega. Omega is the omega frequency here, the speed. And j is the complex argument, square root -1. So if you put any s with j omega, it makes your transfer function now a complex number for any omega, get its magnitude and phase. So it's very clear that this amplification of the input amplitude depends on omega, and this lag depends on omega, right? Depends on how fast you move your input. And this plot of the magnitude versus omega is what we call the Booty plot. Sometimes we have a peak here if we have a resonance frequency or something. And you can imagine that it has to be decreasing all the way. Why? Because like what we described, if you have any system, airplane or whatever, and you're giving an input very, very fast, the system will not feel anything, which means will not give any output. Will give an output with zero amplitude. In other words, it will take your input amplitude multiplied by 0. So this guy is 0 for very high frequency. Okay? This makes sense. And also, the phase is usually negative. So it starts here with 0 phase, meaning 0 lag. If you start oscillating, no matter how slow, you will have some lag. Okay? And so on. Any question about that? So this is what you learn in 170 here, 170, dynamical systems. Why I'm reviewing this? Because to me now, I know that my CL alpha curve is not 2 pi alpha anymore, but it's a dynamical relation. It has a transfer function. And if you're given a transfer function, this is the Booty plot, right? If you're given a transfer function, you can draw a Booty plot, which gives you the dynamics. And by the way, it's vice versa. So this is the very straightforward problem that you have in your undergrad. Here is a transfer function, plot the Booty diagram. But we can do it the other way around. I don't know if you did it or not, but it's not typical to do it. But it's a very standard wave system identification. We get the Booty plot, and from it we construct the transfer function. So this is what Joseph researched. He constructed this experimentally for the unsteady aerodynamics of high angle of attack, and from which hopefully later on we will get the transfer function. So these 4 ways of representing linear dynamical systems are equivalent. Transfer function, state-space model, step response, frequency response, they are equivalent. If you have one, you can get the rest. Okay? Judorson 1935 NASA report, he developed the frequency